for the invitation. Right. So thank you very much for the invitation. And well, I've been really enjoying the other talks, so thank you as well to the other speakers for this. So it's been very interesting. So today I will speak about destabilizing curves and stability on surfaces, and all of the original parts of this work is joined with Sohaib Khalid from SISSA. So the main idea of the talk today is essentially to try and look at some very big and difficult questions and try to then clarify them as much as possible in a simple, very simplified situation, hoping to inspire deeper insights into the general cases. So the questions of interest that I will look at today. So we are of interest in stability in Kähler geometry in general for different geometric PDE, but maybe predominantly still for K-stability and for questions related to Gaussian-Donaldson conjecture and all of this kind of circles of ideas. So the first one is very broad, so it's about effective existence criteria. So finding good existence criteria, that's exactly what Gaussian-Donaldson conjecture does for the constant scalar curvature, Kähler-Einstein equations, and so on. And we have seen previously also in this session, we have seen Jean-Paul speak about when the K-energy functional is proper. There are many ways of approaching these kind of questions. It's a very, very big topic. Sometimes, for example, in toric and toric-like settings, we have effective existence criteria where we can understand better what is going on, but largely there are still many things to clarify that are rather mysterious about the behavior of these test configurations and stability notions in Kähler geometry. And in particular, one of the hot topics related to this that has been emerging is the one of finding various kinds of optimal destabilizing objects. So whether optimal destabilizing test configurations or perhaps a valuative notion has been popular recently, and so on. So this is something that I think many of you have experience with, and something that you are led to try and better understand stability. So the second topic is wall chamber decompositions, which certainly will make you think of Bridgeland stability, where this has been highly successful, and we look at wall crossing phenomena and all of these things. But recently, there has been this interest in looking at wall chamber decompositions, analogs of these for some geometric PDE. So, for example, for the CSEK equation varying the complex structure in some recent work, or as I will talk about today, for some other geometric PDE. And the third question is perhaps one of the more subtle ones in stability theory, which is to compare these uniform and non-uniform stability notions, which well, it's related to understanding in-depth stability notions for various reasons. And actually, it will also turn out that this last part can be viewed as a sort of special case of wall crossing phenomena as well in the second, and we'll explain later. So with that said, our goal is to clarify these big, difficult questions in the best setting that we are able to. So we want to clarify these questions in the simplified context of various families of geometric PDEs, so including the J equation, the deformed Hermitian Yang-Mills equation, which thankfully Kähler has introduced already very nicely. And also all of this will work for some recent extended formalism called the Z critical equation. And all of this will be done in dimension 2 during the talk today, as I said, with the goal of hopefully inspiring a deeper understanding also for, in the long run, for K-stability. So let's just, first we'll call the setup. So I will always work if X omega be, so X is my compact Kähler surface, and omega and theta will be two Kähler forms. Sometimes, very rarely though, during the talk, I will ask that these omega and theta are in rational or integer cohomology classes. So that would correspond to fixing instead two ample line bundles or ample Q line bundles. on X, and the connection would then be this, that we would think of theta as some form representing the first term class of H and of L. Okay, so let me go through these different equations very quickly that I want to study. So the first one is the J equation, which was introduced by Donaldson almost 25 years ago. So this would correspond to solving, so you take these omega and theta, and you want to find so you fix theta, you want to find some omega such that the omega trace of theta is constant. And this can be rewritten rather simply. So I really just fix everything on surfaces now to be able to give a nice and easy presentation as well here. So then it would correspond to this equation, theta wedge omega phi is proportional to omega phi squared, where omega phi is just this standard notation, meaning omega plus ddc phi, where ddc is I d bar. So this is the space, and phi here is then in the space of Kähler potentials, which is the space over here. And c is the only possible cohomological constant given by integrating both sides of this equation. So it's some real number given as an intersection number. So this is certainly an equation of independent interest, but I want to underline that coherently with my main motivation on the last slide, it's somewhat related to the constant scale curvature problem. So if we wanted to compare this to the CSK equation, the best we would typically do is to fix this auxiliary form theta to be in minus of the first term class of the manifold. So this would, for example, corresponds to taking theta equal minus the Ricci curvature form of omega. So then the J equation would look like this. So I just put theta equal minus Ricci of omega. And on the CSK side here on the right, you would get the equation scalar curvature of omega phi is constant, which rewrites in this way, where these constants c and c theta omega are related. So one is, I believe, minus the other. I got the signs right here. But the signs are not important. What's important is that they look at first glance very similar, although they are actually less similar than they may look. So on the right here, we have an elliptic PDE, as you will all know. And here you have actually a parabolic PDE. And my favorite way of viewing the similarities and differences between these equations is to look on the side of properness of energy functionals, so as Jean-Paul did in his talk as well in length. So then we know that existence of CSK metrics is equivalent to properness of the K energy, which I use a different notation compared to previous talks here, but I denote it by M for the Mabuchi K energy functional, which decomposes as a sum of an energy part and an entropy part. And this one should be coercive in terms of Aubin's J functional. And this is true then on the space of Kähler potentials. And if I then want to study instead existence of this quite a bit simpler J equation, then this would correspond to singling out this energy part and asking properness only of the energy part here on H. And this means, since the entropy is always positive, this means that if you have properness on the J equation side, then it implies properness of the K energy, but in general, the relationship is not at all that clear, since the entropy, many of you will know, is typically very, very hard to understand and is not a big obstacle to work with, especially on the analytic side here. So there's some relationship here. Moreover, the J equation is also related to the deformed Hermitian Yang-Mills equation, which we have seen is also of independent interest. And as Kähler explained in the talk, by the way, this also has some relationship emerging with coupling it with CSK. So the deformed Hermitian Yang-Mills equation, I'll just say rather quickly. So it looks like this. So so here you have these two real forms, theta and omega, and then you construct out of this a complex form by taking theta plus I times omega phi. You square it, multiply it with e to the minus I, then some real cohomological constant here, and you ask if the imaginary part is 0. This was introduced by these people here in around 2000 as well. And this of importance in mirror symmetry and string theory. as Carol has explained. So as Carol explained as well, this J equation is then realized as the large volume limit of the DHYM equation. So when we rescale omega to R times omega for R very large. And finally, for the purpose of this talk, so in our paper, we talk a lot about this Z critical equation, but for the purpose of this talk, I just want to mention in the periphery that at some point later, I will just mention that this is a special case of the Z critical formalism, which was introduced much more recently, 2020, by Dervin McCarthy and Seknen. And it looks rather similar to the DHYM equation, where here you have a so-called polynomial central charge. But so all you need to sort of keep in mind about this is that it expects to be a PDE analog of Bridgeland stability, hence also the terminology polynomial central charge. And it depends on this sort of heap of parameters here, where beta is some Kähler class, this is some vector of non-zero complex numbers, and U is some element of some homology ring. And this really parameterizes many different geometric PDEs, so whole continuum of geometric PDEs. So really we are studying on surfaces a large family of geometric PDEs in this talk. Okay, so with that said, let's get to the first topic, which is that of effective existence criteria for the J and DHYM equations, and also Z critical, but I will just present it this way. And the idea is to use something called destabilizing curves to create these existence criteria. So before I get to stating the main result, let's just recall very quickly what's known. So we have this schematic drawing here, this common triangle where existence is known to be equivalent by the work of many people, by the way. It's equivalent to uniform stability in each of these cases. And this is in turn equivalent to some numerical condition based on slope stability. So very quickly, since we are in surfaces, we have a privilege of being able to actually delving into these details rather easily. So slope stability here would mean that take V some irreducible curve on X. You view V cross 0 as an element inside X cross P1, and you blow up X cross P1 along V cross 0. You get this, I write it curly X sub V. You have an exceptional divisor, and you can construct a relatively Kähler class of this form. So you pull back omega from X along these suitable maps, and you take minus a small enough multiple of the exceptional divisor associated to V. So small enough here means that kappa ranges from 0 to the Seshadri constant, but I write kappa bar sub V here associated to this curve. And then this gives a relatively Kähler test configuration. So in the honest sense, this is what we would use to test for in stability, which I write X V kappa. So it depends on the curve and it depends on this kappa as well. So then the proposition in the first paper of Lejmi-Zekidi introducing J stability, they have this proposition expanding out the non-Archimedean functional. So this F here is what you would think of as the non-Archimedean functional of theta omega. So it's the non-Archimedean functional that we wish to evaluate test configurations in to define J stability. So this F expands as a first order term here. So if V is dimension P, so for just 1 second, I go to the higher dimension, but I'll come back to surfaces. So if V is a dimension P reducible subvariety, then the first order term is this, then it has higher order terms. When kappa approaches 0, of course, on surfaces, we can get this rather explicitly. But looking at this first order term, the conjecture of Lejmi-Zekidi was actually that in order, sorry, I'll go back. So in order for this F to be always positive, so to be stable, then it's necessary and sufficient, they conjectured, that only the leading term is positive. So the conjecture would be that the J equation has a solution if and only if this leading term is positive for all curves and for all dimensions P ranging from 1 to the dimension of X minus 1. So going back to surfaces, this was already known by, so now this has been proven, by the way. It's a theorem due to Gao Chen, Data Pingali, and so on. And But on surfaces, it was known long ago. So it was a theorem already by Chen, Shushong Chen, not Gao Chen. That the J equation has a solution if and only if this integral here is positive for all reducible curves. So this will be important for the rest of our talk, but really we are integrating some suitable 1-1 form depending on our initial data, and we vary this over all irreducible curves. And we have a solution if and only if this kind of integral is always positive. And this happens by Nakai-Moshe criterion. You can easily see that this is equivalent to this being a Kähler class. This is for parentheses. And the same for the dim equation, same principle goes. Existence is equivalent to integrating over some other form depending on initial data, where C tilde is defined like this. So by the way, this is not the optimal way of writing it. So here I assume I'm in the supercritical regime, which would mean that this is always a non-zero number. But there are ways to improve on this writing here. But essentially, the point is that you integrate some 1-1 form over all irreducible curves. And this is, again, equivalent to existence. And the same thing actually holds for the Z-critical equation. So in each case, this is the fundamental principle. You have some form associated to your equation and your initial data, and you want to see if this kind of integral is always positive for all such reducible curves. So what about effective existence criteria? Well, the idea of this paper, so the first central idea of what I'm talking about today is that, we would like to understand the set of all these curves for which this kind of integral could be non-positive. This is what we would call a destabilizing curve. So we say here, have a definition down here, that V is a destabilizing curve if and only if for the given tau associated to our equation, this one is non-positive. So we want to understand the set of all destabilizing curves as a function of the PD and the initial data. And the reason that we want to do this is, of course, that they are the only relevant ones with regards to stability. So any curve that is not destabilizing, any curve that could not appear as a destabilizing curve, we can just simply discard, and it's redundant for testing stability. So the main result that we'll actually show is that there is, in fact, a finite number only of candidate destabilizing curves. And this will give us a finite number of conditions to check for stability, rather than all of this infinite number overall curves, or even worse, in K-stability, you have to test for all test configurations. So this yields our main result here. So first, I write it down for the J equation. So the question is, which are the relevant curves that we need to consider for this numerical condition, whether we consider the J equation, the dim equation, or the Z critical one. So the main theorem for the J equation would read as follows. So this is actually not how I wrote it how we wrote it in the paper, but I wrote it out a bit longer for the purpose of this talk. So the first part is that if you're on a compact Kähler surface, then associated to your X and your omega and your theta Kähler forms, there would exist a finite set of curves that happen to have negative self-intersection, such that this kind of integral is non-positive, so destabilizing curves. So finite number of destabilizing curves, and actually we even have control of this number. It's less than the Picard number of the surface. Okay, and so this is already giving some kind of effective criteria to test, but actually we wanted to do more, because especially when we're going to get to the part about wall crossings, wall and chamber decompositions, it's actually important to ask how this set of curves depend on theta and omega, because for now in the first part they really depend on theta and omega, and they could depend on very bad ways. We perturb a little bit and you need a whole set of different curves, which would make then this kind of theorem much less useful. However, we have here that the set of curves can essentially be taken uniform across compact subsets. So for any given compact set inside so this CX here is the Kähler cone, so the set of classes omega, bracket omega represented by a Kähler form. So for any compact set in here, so for any compact set of initial data, essentially, there exists a set of curves depending only on K, such that the following are equivalent. So the same statement holds, but I write out here summary of what was known and what we add here. So Chen already showed that the existence of a solution is equivalent to testing this kind of condition over all irreducible curves. And we then say that there is this global in K set of curves such that it's always enough to just integrate these forms against this finite set of curves to test stability. So there's a deformed Hermitian Yang-Mills version of this as well, which looks as follows. So here I kept the slightly shorter version, but the principle is exactly the same. So if you fix any compact subset inside the space of initial data here, then you have a finite set of curves that have negative self-intersection on X, depending only on K, such that solving the equation is equivalent to checking a finite number of conditions where C tilde omega times omega minus tau. So this is this other 1-1 form relevant for the dim equation. And here this 1 equivalent to 2 is proven by Collins, Jacob, and Yang. So there are many things to say about this kind of statement. First thing, by the way, we have a corresponding one also for the Z-critical equation. I can show it to you later, if you wish. But so there are many things to say. I'll say just 2 things for now. So first one is that it implies existence of solutions to the dim equation. So if you have no negative curves. So if you have no negative curves, then the dim equation can always be solved for any underlying data. Similar thing for Z-critical equation. And for the J equation, but for the J equation, this was already known. And the second and more important one, in my opinion, is that this yields a computable finite number of conditions. So of course, it's theoretically important, but on top of it, it actually turns out that this is a computable condition. If you know the Zariski decomposition, but on surfaces, there's actually an algorithm for this. And the reason is the following principle, which is that the set of destabilizing curves will, as the proof on the next slide will show, is actually going to be contained in the so-called negative part of the Zariski decomposition of a suitable 1-1 form, which is just these forms appearing here in the statement. Taking the negative part of the Zariski decomposition of these, you will get these curves, and they will work globally. So just a very quick outline of the proof here before going to the next topic. So the very first point that I chose to include here is actually the real crux of the matter. So the new observation is that if you take any initial data, so in this case, we're in the simpler case of the J and dim equations, so the initial data are manifold and 2 Kähler forms. Then you consider the associated 1-1 form, such that existence is equivalent to integrating over this. So for the J equation, we had this one. For the dim equation, we had this. Then the key observation here is that if you look at the class of this form, so then this is always a big class. So meaning then that it can be represented by a Kähler current. So being a close positive 1-1 current that's bounded below by a small multiple of a Kähler form. So, okay, so this is the observation. But for all of these equations, so the J, dim, and Z critical, this kind of, and for any initial data, this class is always big. And then we note that any big 1-1 class has a Zariski decomposition. So now we're not talking the most classical sense of a divisor, but more in the sense of Buxom, which would also exist in higher dimension, where here I've dropped the brackets, by the way. But so this is now a class, 1-1 class. So it decomposes into a nef part and a negative part. So this nef part will always integrate positively or non-negatively rather against all curves. And then we have a negative part. And the negative part is a finite sum like this, involving these some curves EI and some positive numbers AI. where these curves EI have some known properties, namely that this intersection matrix is negative definite, and the EI are linearly independent in the non-severity group. And from this linear independence, you get this bound that actually the number of curves that you can have is bounded above by the dimension of the non-severity group, which is the Picard number. So, yeah, and then finally, it remains to check that if you have a destabilizing curve, so here I just do a case strictly destabilizing, it's easy to see. And then if you're not strictly destabilizing, so it's equal to 0, you need to perturb a bit. That is the same argument. So then this destabilizes if and only if by the fact that this is NF, so always integrates positively. So the integral along the negative part has to be negative. So this means something like this, that the sum of AI, positive numbers, times V dot EI is negative. So this one has to be negative for some EI, and this will actually turn out to imply then that V is equal to EI for some of these EIs. And okay, so this is the outline of first part of the proof. So given some initial data, theta and omega, it gives you this finite set of curves through Zariski decomposition. So it remains to check the uniformity across compact sets. And here the idea is that if you take a compact set of initial data, so compact set of classes of theta and classes of omega, then you can look at the map sending this initial data in K to this class here, which is the class of these forms that we are looking at. So now I'm writing it for the J equation, but again, the proof is the same. And this we said was always a big class, but actually this is the continuous image of a compact set. So the image, we can call it K bar, and it will be compact as well. And then this set associated to K prime. So if you take the union of the negative parts of all the tau, classes tau in K prime, then have some brackets here with mismatch, but that's okay. So then this would be the union over all destabilizing curves associated to each of these initial data. Then actually this is a finite set. And the way to see this is simply that being a compact K prime inside of this big cone, it will be contained in the convex hull of some number of pseudo-effective classes, so illustrated somewhat like in this picture. So tau can be written as a linear combination of these generating classes here, tau I, and then we will conclude that the negative part of tau will be included in the union of all the negative parts of tau I, but there is a finite number of these tau i's, and hence we even get a bound actually that the number of curves that we need is bounded above by m times the Picard number, where m was the number of classes that we need. Okay, so that's the sketch of the proof. So now this uniformity, as I said, this actually turns out to allow us to talk about the next topic, which is wall and chamber decompositions. So first, what is a wall and chamber decomposition? What do I mean by this? So this goes back to Bridgeland, and I just take a sort of sample result from one of his papers here, in this case from 2003. So he showed existence of a wall and chamber decomposition where he decomposed the set of all stability conditions on X. He was working with here. So he was working with this D of X, some derived category of coherent sheaves. So it was a much more algebraic setting, of course. But so what he showed was the existence of a finite collection of real codimension 1 submanifolds of this space of stability conditions, such that it decomposes this compact set. So he chooses a compact set B, I should say, inside the set of stability conditions, and it decomposes this compact set into chambers. So you can see this sort of sketch picture. So if you place yourself in any of these chambers, it has the property that if one of these objects, so coherent sheaves, is in this case semi-stable, but you can think stable. If you want, so if it's stable for some stability condition, then it's stable for all other stability conditions in this chamber. Okay, so he varies the stability condition, and any objects. So for this given object, it's stable with respect. If it's stable with respect to one stability condition in a chamber, then it's stable with respect to all others in the same chamber. So how do we view our main theorem in this kind of light? So how can we make a comparison? So for this, we can look at the space of all initial data. So looking at all initial data corresponds in a way to varying the geometric PDE, right? So this would be even clearer if we looked at the Z-critical equation. But so we think of this varying initial data or varying our underlying PDE. And we look at all the initial data such that let's say the DHYM equation is solvable with respect to this data. Then you take your compact set and you restrict this set U here to K, and then it's cut out by the finitely many conditions of this form, as we saw in the main theorem. So E1 to EL are exactly those curves given by the main theorem. And then, more importantly, then the boundary of this set is defined precisely by a finite number of conditions that, this kind of integral is 0 for one or more of the EIs. So making the comparison with Bridgeland, then, so with this initial discussion here, we would get that this defines a codimension 1 submanifold, finite number of those, and it will decompose this compact set into chambers such that with respect to this initial data, in the same chamber, all equations are either solvable or all equations are not solvable. By the way, this boundary also forms a real algebraic set, which is something that we definitely don't have this kind of picture in larger generality in, for example, K-stability or so on. So, as I said, this kind of result is really only, complete when you look at the Z-critical equation. So let's go over for a second. So for the Z-critical equation, now let's compare this to Bridgeland stability. So on the Bridgeland side, we decompose some compact set inside the space of stability conditions. And on the Z-critical side, we would decompose some compact set in this, complicated looking set, but which we should think of as the space of geometric PD of Z-critical type. So we vary the underlying equation. And, conjecturally, solvability of these equations should be equivalent to some kind of stability condition. So in a way, we can also think that we vary the kind of stability condition that's underlying here to be Z-critical ones. And then, so this is a rather long statement, so I won't read it all, but what it says is basically that you fix some, so you have this set of the space of all these parameter values parameterizing geometric PDEs. You look at a suitable subset of this for which the Z-critical equation has a solution. You restrict it to K, and then this set is cut out by a finite number of conditions, where this tau Z is again some suitable 1-1 form. I don't write down what it is. And this finite number of conditions is then indexed by a finite number of curves, which are precisely the one coming from the main theorem through Zariski decomposition. And it has this property that we can compare exactly with the Bridgeland side here, that if you take any connected component of this kind of set, so the one cut out by these equations, then so your equation is solvable with respect to, so if one equation is solvable with respect to the initial data that we have fixed, then it's solvable with respect to all the other equations in the same chamber. Okay, hope I made this clear. So if not, let's look at a simple example. So we can look at P2 blown up in 2 points. So then we get this kind of picture. So we have two of these boundaries going here, defined by two real algebraic equations here, so being 0. And what we've done here, so just saying schematically, is we've just fixed two line bundles on P2 blown up into points. And we ask, when can we find a solution to Z critical equations in those line bundles? So L1 and L2. So then you get this kind of picture, and you see that on, for example, this one is the line related to L1. And so on one side of this line, you can always solve all of the Z critical equations for all of these parameter values. And on the other side, you can't solve it. You get these chambers where in some you can solve both L1 and L2. For some equations, you can't solve the equations, any of the equations in L1 and L2, and so on. So I wrote down here a bit more of the details of this example as well. So, okay, so if you blow up P2 in two distinct points, you get two exceptional divisors, E1 and E2. You write H with a pullback of the line. Then you have three negative curves, E1, E2, and a strict transform T of a line passing through P1 and P2. You look at L1 and L2 like this. And I should say this is a rather sort of randomly cooked up example. So you can certainly do many other things here. It was more to try and get some suitable complexity of the picture. And then you consider Z critical equations defined by these central charges parameterized by some complex number S. Okay, so you write down some parameter values. So each parameter, each value here corresponds to a different equation. And then we get these conditions that need to be satisfied, parameterized by this infinite number of curves, and we get this kind of picture, which is then a slice, of course, of the full wall chamber decomposition. So this is just the slice when we vary this parameter S. Okay, so to summarize, we really vary multiple things, which might be confusing at first. So we can vary the initial polarizations where we're trying to solve our equations, but we can also vary the underlying PD, or the other side of the coin, the associated stability notion. So in this picture that we had in the example, we fixed the initial polarizations and we varied the PD. But I can also get a similar picture where I ask to vary the initial polarizations instead. And then what would it mean to go from one chamber to another? This is one of the, of course, most classical questions in Bridgeland stability. What happens with wall crossing? So then it would correspond basically to being uniformly J stable, let's say, if we focus on the J equation, inside the chamber. Then on the boundary, you would be J semi-stable, and then you cross into being perhaps again uniformly J stable or into being unstable. And so understanding what's happening on the wall is one of the most subtle and classical topics. And this actually would then be possible to interpret in light of this question then, is uniform and non-uniform stability equivalent? So that would correspond then to say, when you're on this wall and you're J semi-stable but not uniformly, are you also J stable or not? Okay, so comparing these things, and this also strongly related then to optimal destabilizers, really two sides of the same coin. So the first first observation to make is that if we focused, as we did before, only on slope test configurations, then for sure they can never satisfy, they can never realize a zero of this non-Archimedean functional if we assume that we are semi-stable. So again, if you are on the wall, you can never have such a slope test configuration that realizes the value 0. So a non-trivial one, of course. Trivial one wouldn't be able to satisfy this. And the reason for this is just this explicit computation that we can do because we're on surfaces, that this non-Archimedean functional would be of this form, depending on A and B. And so kappa, again, being this parameter that we vary between 0 and the Seshadri constant, where A is just this initial condition that we see all the time here, and B is minus this constant times the self-intersection of B. So you can argue, so basically, by a simple argument, you can argue that it's incompatible to say that this F should always be positive for all K from 0 up to the Szadri constant, and to say that it should realize 0 for some strictly positive kappa. Okay, so this is not the full argument, but this you can believe, I think. So if you restrict, so the conclusion is that if you restrict just to slope test configurations, then it looks like whenever you're J semi-stable, then this kind of test configuration never realizes a 0. So rather it's strictly positive all the time. So it would mean that when you're J semi-stable, you're also J stable. On the other hand, J semi-stability is a closed condition, and uniform J stability is an open condition, so they cannot be equivalent. So in other words, it looks like restricting to slope test configurations, at least J stability wouldn't be equivalent, would not be equivalent to uniform stability. But of course, this is a sort of silly example because we expect any optimal destabilizing one to be perhaps among the singular test configurations or more involved test configurations. So how about the other ones? So here we connect with some very nice recent work of Hattori, where he exhibited, he found one example of a polarized surface, which was J-stable, but not uniformly stable. So here we enter the sort of projective surfaces. But they found such an example, which was, to my knowledge, the first one. So this is very nice. And so it's natural to understand if there is some kind of underlying pattern to this. Okay, so we found one example where J stability is not the same as uniform J stability. So does this happen often? And why does it happen? And so on. So let's try to see if we can understand something about this. So the main theorem we were able to obtain tries to clarify this. And it essentially says that uniform and stability is almost never equivalent to J stability. So it will say that except for the case where you have no negative curves, so as long as you have at least one negative curve, then no matter what initial manifold you choose, so projective manifold, projective surface that you choose, you can find on this surface some ample line bundles that for which then we have J stability, but not uniform J stability. So any projective surface, you can find such examples. And the idea of a proof is sort of at some point using Hattori's techniques, which has a very nice theorem about decompositions of J stability into lower dimensional conditions. But so but the new part here is to consider that if you have a negative curve, projective X, then we can actually find a rational class omega prime, which is Neth big and not Kähler. And we can also, for free, normalize it in a suitable way that we want. Then we can look at this kind of class. So interpolating between our new rational class and theta. And this one will also be rational as long as this T parameter is rational. Then we combine this with some knowledge from a previous work of mine on optimal lower bounds on Donaldson's J-functional to see that actually if we take T to be equal 1/2 here, then this is precisely the unique point where we are J semi-stable, but not uniformly J stable. Then we're really on the wall. Being on the wall corresponds to T equal 1/2. Now this is a rational class, and so we can, with just a little bit of work, we can apply Hattori's mechanism to see that we're not only J semi-stable, but we're actually also J stable, but still not uniform. So then we get this kind of examples. And conversely, what happens if you have no negative curves? Well, then it's a standard argument, I believe, to see that, in fact, then you always have solutions to your equation, and you're always uniformly J stable for all data, XLH. So either you have no negative curves, you're always uniformly stable, or you have these kind of examples where J stability is not equivalent to uniform J stability. So clarifying this to some large extent. And as a related flip side of this, we get non-existence of optimally destabilizing test configurations. So if you take any smooth projective surface, any Q-line bundles, then there can never exist an optimally destabilizing test configuration. This is again a combination of Hartley main theorem and giving this finite number of curves, and some calculus using stability thresholds here, showing that this kind of quotient of this non-Archimedean functional over its norm always is strictly larger than its infimum. And so to finish off, I just want to say one word, that even though uniform and non-uniform stability for the J equation turns out to not be equivalent in most cases, and optimally destabilizing relatively Kähler test configurations never exist, then we do have at least something, and this would be what we could call optimally destabilizing curves, and they can actually be characterized. So let's see what we mean by this. So we can do this more generally, but suppose for simplicity that we are J semi-stable. When a curve is said to be optimally destabilizing, so J destabilizing or J negative, so word we use in our paper, if this kind of integral is equal to its infimum, which is exactly 0 because we were semi-stable. And similarly for the dim equation, so we say that we are optimally dim destabilizing if this kind of integral is equal to its infimum. And then we can actually characterize this. So the theorem is that the set of optimally J-negative curves is exactly equal to those curves that intersect in a 0 way with some class A. And this class A we can exhibit explicitly. So this A is supposed to be a Neff but not Kähler class, such that omega is on the line, so this convex combination here, between A and theta for some t between 0 and 1. So you might say this is not always possible, that's true, but it's always possible up to rescaling this omega, which is harmless for this purpose here. So you take this boundary class A, and basically what you have is that the optimally J-negative curves are exactly the ones that violate the Nakai-Moishism criterion here, actually, for this Neff but not Kähler class. And by the main theorem, by the way, we can see that the cardinality of this kind of classes violating the Nakai-Moishism criterion is bounded above by the Picard number of the surface. Again, so this is a combination of the main theorem and some other results here. Fine. So, and you get, then you can ask about the dim negative curves, and we know that the J equation is the large volume limit of the dim equation. So there might be some relationship, and actually it turns out that the set of optimally destabilizing curves for the dim equation actually coincides. So it's exactly the same set. So it coincides with the set of optimally destabilizing curves for the J equation. So with this, let me just take the final slide. So in conclusion, this kind of techniques using the Zaliski decomposition, using the numerical criteria, can, at least on surfaces in this simplified setting, give answers to these questions. It gives computable existence criteria, gives wall and chamber decompositions, which is the first of this type, when you vary the PDE rather than what Bridgeland was doing. So this is very much in line with the ideas, of course, that Durbin, McCartney, and Seknan had in their paper introducing the Z-critical equations in this direction. And importantly, this is because you have this global property in K of the curves we obtain. And then for specifically the J equation on surfaces, we answer this question that uniform, non-uniform stability is non-equivalent generically, and there can never exist an optimally destabilizing test configuration. However, there are these optimally destabilizing curves. And so the program now is really to ask how this affects and implies, and what it implies for K-stability and other geometric PDE that we might be interested in. So can this inspire some deeper insight in larger generality? For example, comparing K-stability, uniform K-stability, wall chamber decompositions in other criteria, other contexts, or this computable existence criteria. So this, sorry, I'm a bit over time. So with this, I want to thank you all for listening, and thank you as the last speaker. I want to also thank all the other speakers and also the organizers for putting together this very nice event. So thank you.